All right, so welcome to General Biology. The design of this course is going to be a little bit different than what you probably have experienced in most previous science courses. Typically, we just start with chapter 1 and walk through 16, 18, 20, whatever chapters and talk about terminology and look at diagrams and say memorize this and remember that, and that's it. In the big picture, it's might not be the best way to learn science, especially for somebody who's not a scientist, who isn't going into science. What non-scientists need to do is learn science from an application perspective. Why do I care about this? How does this relate to me? Why is this important? Instead of memorizing a bunch of facts and information, regurgitating them for an exam, and then forgetting it. So instead, we're going to go at this from a completely different direction. We're going to go at this from a relevancy-based perspective. Why is science important to you? Why is the process of science important? That's what I want you guys to understand. Not memorizing terms and things like that, but when you walk away from this course, you understand these ideas, these topics, and you understand why they're important to you. Why does it have meaning? Why should I remember this 15 years from now? And how does this apply to my life? So to do this, we're going to approach the resources in the course very differently. We're going to be working with what are called the relevancy modules. So if you go into the course in Connect, the McGraw-Hill platform, Connect, you're going to go into the relevancy modules and you're going to click on the appropriate module, read through it, and then look at the lecture. Watch the lecture, listen to the lecture, take the notes from the lecture. And then we'll have other things that we do with each module. There will be labs, there will be quizzes, there will be other things that I've built into this course to help you guys understand the importance of these topics and the relevance of these topics. All right, so to get started, we really want to understand what is the process of science. How do we know it's real? How do we know we should trust it? There's a lot of fake information out there. How do you know what's accurate? People are trying to sell you stuff all the time that take this pill, it'll make you skinny. Rub this on your head, it'll make your hair grow back. Do this, do that. It's all going to work. Is there science behind that? Or is somebody just trying to make money off of you? People manipulate science. Well, not every scientist agrees that climate change is occurring, so we shouldn't do anything about it. Do we trust that statement? So the example we're going to start with are these things called Himalayan salt lamps. I bought one. Bought it as a gift for my wife. 60 bucks. Does it have science behind it? It's making a lot of claims. It's making a lot of scientific claims. It will do this. It will do this. It will do this. But is there any truth to what it's claiming? That's what I want us to be able to evaluate. That's what I want you guys to think about. I want you to pause and say, okay, wait a minute. Let me not just get all hyped up and excited about this cool thing that's out there. That's going to do this. That's going to do that for me. Don't buy it because of emotion. If you think it's going to make you feel better and healthy, buy it because the science is supporting that it's going to make you feel better and that you're going to be healthier. So let's take a quick look at this idea called scientific literacy. So when something is presented as having scientific support, we want to know, is the information valid? Does it have scientific information? Is there evidence to back up the claim? So in order to do this, if we're going to make a claim that we say is scientifically valid, We have to run the scientific method. Everybody's done this. You call it problem solving. Why won't my car start? Let me figure it out. My car didn't start because. Do you have science to back up that statement? So the overview of the scientific method. You start with a observation. My car doesn't start. It worked. I got to work, drove here, 33 miles, got to work, left work, now it won't start. Based on the observation, you come up with a hypothesis. Now, a hypothesis is a question or a guess about the observation. So I want everybody to take a moment, write down your guess as to why a car won't start. So you're supposed to be writing it down now, okay? Write it down. My observation or my hypothesis that I'm going to use is I think I have a dead battery. Now, some of you may have written the same thing, dead battery. Some of you may have said out of gas. Starter's broken. Alternator's broken. Spark plugs are bad. How many different hypotheses could we come up with about the same observation? Now, fixing a car, you want to figure it out quickly. But when we have big picture stuff, we want lots of hypotheses about the same observation. Lots of ideas, lots of questions. Each hypothesis, we want to design an experiment to test it. Now, really, we want to design a bunch of experiments to test the hypothesis. So, if I'm going to go with battery, think about the experiments I could design to test my battery. Could ask the person next to me, hey, can you jump my car? I got cables. Let's see if that kicks my car, that puts enough electricity into it that I can get my car started. That's one experiment. I could try to turn the lights on. Is that a valid experiment? I could pull the battery out, take it down to AutoZone and test it. Have them put on a tester to see if the battery's got life in it. So I want to have a bunch of experiments to test the hypothesis. So start thinking about the big picture here. If I have 5 hypotheses, maybe I have 3 experiments per hypothesis. All of them are being tested. All of them are being run. I collect data on every experiment that I run for every hypothesis. And I collect all this data. And what will now happen is either my data agrees with my hypothesis. Yep, tried to jump the car, didn't work. Battery shot. Or the data doesn't agree with it. No, battery's fine. Got it tested. They said it's full charge battery. So now I'm kind of stuck. What do I do next? Because I want to get an answer. I want to figure out my problem. I need to solve my problem. When the data doesn't agree, we have some options. Redesign the experiment. Run it differently. Change some variable in the experiment. But redesign it. Collect your data. See where you're at. Or maybe redesign the hypothesis. You can. That's not cheating. You have the answer. You have data. Change the hypothesis so the data supports the new hypothesis, what we'll call hypothesis B. You're not done though. You don't get to go, see, I'm done. I have an answer. I'm going to write the question to fit the answer. Finished. No. Rerun your experiment. If you've redesigned the hypothesis, you still need to rerun your experiment. If your data does agree, you still need to rerun your experiment. Now, fixing a car, no, we're not rerunning it. We're done. Car's working, back on the road. But in science, I'm going to rerun my experiment multiple times. I'm going to have others run my experiment to confirm. I want lots and lots and lots of people all around the world running these experiments, collecting the data to see, does it continue to support? Does it reject? Now, the reality is, in the big picture of the scientific world, you may have thousands of experiments testing hundreds of hypotheses. Will every single one of them match? Will every single one of them support? Probably not. But at a certain point, you're going to say, I have a lot of data. I have a ton of data that supports my experiment. That supports my hypothesis. 99% of the data collected supports. Do we accept this? If we get to that point, we then move to where we can call this thing a theory. Now consider people who may say, well, not every scientist supports this theory, so it's not really valid. Okay. Let's put that into the military. For those of you who've served or who have experience with the military, I had a student years ago who was a former service member, had served overseas in Iraq. He said, yep, 90% of the military intelligence came back, told the commander, this road has IEDs on it, bombs. A smart commander listens to the consensus. Yeah, there's one person who said they didn't think there were bombs on that road. But you got 90%, 9 out of 10 are saying there's a problem with this. You listen to the majority. Would a good commander say, not everybody agrees, let's go down the road? No, they wouldn't. So in science, there is always going to be somebody who doesn't agree with the data. And that's okay. But there's a certain point where you say, this theory is supported by enough fact, I'm going to trust it. Gravity. Can we prove gravity absolute 100%? No, because I can't drop everything in the world to see if it goes to the surface of the earth. I trust the theory of gravity. Had a student once who said, if you don't believe it, it's not true. I said, well, you probably don't want to step off the edge of a building thinking that one time it won't work and gravity won't follow through. So things like cell theory, germ theory, theory of plate tectonics, theory of evolution, and the list goes on and on and on, are all supported by vast amounts of data. Yes, there are people who don't agree with some of these theories. That's totally fine. Just like that one person who didn't agree with the danger assessment of the road. But what does a smart commander do? They listen to the data. That's what we do in science. We listen to the data. We look for flaws. We look for reasons to reject, to negate, to say this hypothesis doesn't work. But when the data confirms it over and over and over, other people confirm it, independently confirm the same concepts, you reach a point where you say, I'm going to trust this. All right. So what I like to do is keep these lectures, these parts, about 15 minutes-ish. So that way you guys don't have to sit for an hour, 2 hours, 3 hours. That's way too long. So each part's roughly around 15 minutes. When you see the title of the module and it'll say part 1, part 2, part 3, those are your hyperlinks to move forward with the next part of the module. So I'm going to stop now. We wrap up here and then click on the hyperlink, start up with Process of Science Part 2, give you another roughly 15 minutes worth of content, and then on to Part 3 and so on. The idea is just so you guys can compartmentalize it and break it down into smaller chunks if you want. You're more than welcome to sit through all the parts in one setting, but this gives you the option to break roughly every 15 minutes.